Welcome back to the workshop for one more example on mathematical induction. In our last video, we observed that sometimes the principle of mathematical induction doesn't quite do what we want it to. We have to refer too far back in the inductive step. So we introduced the strong principle of mathematical induction, which assumes that the statement is true for everything from the base case all the way up to k. That allows us to reach back as far as we need to in order to show that the next statement is true at k plus 1. So let's look at our example. We want to prove the statement that the nth Fibonacci number is greater than or equal to 5/4 to the n for every integer 3 or greater. And to do this, we saw that we had to reach too far back. We hadn't made any assumptions about the k minus 1th Fibonacci number. So we introduce again the strong principle of mathematical induction, where we have everything from the base case to k. That allows us to reach as far back as we need to. So let's look at our proof then. It'll be a bit of repeat from what we did in the last video, of course. Our statement is that the nth Fibonacci number is greater than or equal to 5/4 to the n, and the smallest case that we want to consider is 3. So let's consider that smallest case, the base case. We already showed last time that the base case is satisfied, so let's do that here rather quickly. We let n be equal to 3. We observe that the third, or the nth Fibonacci number, is the third in this case, because we're letting n be 3. The third Fibonacci number is 2, which is greater than 125 divided by 64. How did we get that number? Well, we got that number by taking 5/4 and cubing it. Why did we do that? Well, that's exactly what we wanted here, right? That's 5/4 to the n. So that allows us to say that S of 3 is true. So the base case is satisfied. The next thing that we want to do is look at the inductive step. Now for the inductive step, let's see here, we want to assume that S of 3, S of 4, all the way up to S of k are all true for some integer k. Of course, that needs to be greater than or equal to 3, because the smallest thing we could consider is 3. Now, I could make the statement about what these look like, but I'm not going to worry about that. In our last example, right, we pointed out that if S of k is true, then F sub k is greater than 5/4 to the k. And that's what we want to utilize here. So then, for n equal to k plus 1, all right, we want to show S of k plus 1 is true. So we've got F sub k plus 1. Now, in order to bring this into terms of 3 to a power, 5/4 to a power, we want to write it in terms of things we know compared to 5/4 to a power. So we write it in terms of previous Fibonacci numbers. So this is F sub k plus F sub k minus 1. This Fibonacci number is the sum of the two previous Fibonacci numbers. But both of these are greater than or equal to 5/4 to the respective powers. 5/4. Excellent. Now what I want to do is I want to simplify or rewrite this in such a way that I can express it as 5/4 to the k plus 1. That seems kind of weird, but it is possible. So in this case, the first thing I'm going to do is pull out the common factor of 5/4 to the k minus 1. What I'm left with is I still have one of the 5/4 here. And then I've pulled everything from there, so that's just plus 1. All right, writing that as, let's see here. Let's see. Yes. 5/4 plus 1 is 2.25. Right, that's 9/4. 5/4 to the k minus 1. 5/4. Sorry, 9/4. There we go. And what I can do here is I want to replace this with 5/4 squared. Can I do that? Yeah, I can. And of course, it's not going to be equality anymore. It's going to be an inequality. And I just have to make sure that inequality goes the right direction. So 25, actually I said 25/4. I need 25/16 here. 25/16 is certainly smaller than 9/4. So if I replace this with something smaller, then what I get, my new thing, is going to be smaller. My old thing was larger. So 5/4 to the k minus 1 times 25/16. But this is exactly 5/4 to the k plus 1, right? This is 5/4 squared. So I get two more factors. Thus, s of k plus 1 is true. Once I have that, I can say by the principle, the strong principle of mathematical induction, s of n is true for all n greater than or equal to 3. Therefore, by the strong principle of mathematical induction, s of n is true for all n greater than or equal to 3, as described here, right? S of n, base case is 3. So it's got to be greater than 3. All right, and that's it for this section. We'll actually see a couple more examples of proof by induction in the next section as well, which is applications of some of the things that we've seen throughout Chapter 2. Thank you for your time and attention. I'll see you guys back in the workshop in a little while.